Couple more minutes and we'll start. Okay, I think nobody else is joining. I'll just drop a message. If not, we'll get started. We'll not waste time. And I'll be sharing the PowerPoint. Okay. So if you want, you can take a screenshot or later I will be sharing. All right. I guess about including me, about 11 people are there. So I think we can start. Can you just confirm if my screen is visible and if my audio is audible? Yes. Okay, thank you. So we'll be starting with mechanical properties of solid, right? So the first thing we can do is we can classify solid into two groups, right? And they are either plastic or it can be elastic. Now, what are elastic materials and what are plastic materials? If I apply some force to any material and it regains its shape, all those materials are known as elastic material and the property is known as elasticity. Similarly, if I apply some force to any type of material and the shape retains after I apply the force, these kind of materials are known as plastic materials and the property is known as plasticity, right? And the force that we are applying, right, whatever the force that we are applying, that is known as what force? That is known as deformation force, force of deformation. right? So this is how we can classify the materials or solids. Either it can be elastic or it can be plastic. Now coming to the next part, whenever we apply some force we can measure it, right, at what point it is going to break or something like that, right? For that we define two parameters, one is stress and one is strain, and we have a stress strain graph as well. So this will tell you whether a particular material is going to be plastic or elastic, in what region, and what is the maximum strain and stress it can hold, right? But what are the main things that you have to know from the exam point of view? I guess somebody is joining. Okay, Niharika. Okay, back over here, right? So we define two main parameters, and then I'll be coming to the moduluses. We have three types of modulus. Everything I'll be writing down, and we'll be solving the questions, right? So we define two parameters. One is known as stress, and the other one is known as strain, right? Over here, the definition of stress is the if you apply some force to any material, what is going to be the change in the surface area? This is the cross sectional area, that is known as stress, the ratio of force divided by the cross sectional area, and it is represented by a symbol. What is the symbol called? This is called sigma. I will write down over here. This symbol is called sigma. Okay, and it is F divided by A. And what is the unit of this one? It is Pascal. Okay, so you can write down, it can be Pascal. And what is Pascal equal to? Pascal will be equal to Newton per meter square. So both are one and the same. So if you see PA, so that will be equal to Newton per meter square. You have to remember this one. Okay, this is the SI unit. Now coming to the strain, I'll be talking about the types of it. Okay, so as of now you have to know the main formula, that is force over area, and area is representing the cross sectional area. Now coming to the strain, we have, if I apply any force, it can be I can extend any material or I can compress any material, whatever it is, right? What will be the change in the length divided by the original length? That is known as strain, and that is represented by this particular symbol. And what is this symbol called? It is called epsilon. So I will write down over here, this is called epsilon. This is called epsilon. And for this one there is going to be no unit. You have to remember this one. It is going to have no unit. It is going to be having no unit. Over here it is Newton per meter square or Pascal. Strain will have no unit. Why? Because this is measured in meters and even this is measured in meters, so both of them will be getting cancelled, right? So this is going to be a constant. It will be a constant, and for different materials it will be different. Okay, now coming to types of stress and types of strain, I guess for that let me go to the next slide over here, right? So let me write down types of stress, and here it is types of strain. All are almost similar but with a small difference, right? So let me go back over here. The first one is known as tensile. So you can have tensile stress and tensile strain. Now what is this tensile? If I pull any material along its length, that is known as a tensile force, and whatever the force that is applied, that is your F, and whatever the cross sectional area, this is going to be your A, right? And if I extend this was the length before, right? Now this is extended by small distance, which is delta L. So we can have two types of, from the same thing we can have tensile stress, tensile strain as well. So for both of them I'll be writing down the formula, right? So this is represented by sigma, and what is this? This is the force divided by the area, right? And how is going to be this force? This force will be normal to area or perpendicular. Basically it is going to be perpendicular. And similarly here we can write sigma t, tensile, right? And here it is going to be epsilon t. What is the change in length? It is delta L. And what was the length before? It was L. So this is the formula for tensile stress and tensile strain. Okay, is it clear? Now, coming to the next type. And tensile and compression both are almost one and the same, right? The only difference is what? The direction is only the difference, right? So over here, it is going to be the same thing. If I consider this particular length as L, right? Whatever the small length it is compressed, that can be taken as delta L. And whatever the force that I'm applying towards the material, that is your F. Now once you know your F, your A and your delta A, you can calculate for compression as well, and it is going to be the same thing as tensile, right? The only difference between tensile and compression are what? The direction. So the formula will remain the same. Okay, however the direction is going to be different, so you can plug in a negative value over here. But mainly we classify stress and strain into three parts, that is your tensile, shear and volumetric or volume stress, right? So let us talk about shear. What do you understand by shear? I think you have played Jenga. Do you know what is Jenga? Something like this will be there, right? We keep on, right? And what happens? So for here, if I have any material, right? And can you imagine that all these are atoms, just like your Jenga? If I have a big material, okay, I will write down over here, right? So I have some material this way, right? And just like your Jenga, can I assume that these are made up of atoms? These are made up of atoms, right? Basically, yeah. Now, if I apply any force over here, how was the force? The force was normal to the area. Normal means it is perpendicular, right? This way, right? The area was like this and the force was perpendicular. The angle was 90-degree. If I apply any force that is parallel, meaning that if theta is equal to 0, like this, if I apply some force, right, then what is going to happen? Of course, in a material you cannot see the change, right? But assume that it is a Jenga, then what will happen? So the top part will move, right? Still it will remain intact, but the top part will move. Are you able to understand what I'm trying to say? This one. So if it was like this, any material, and if I apply any force that is parallel to the area, how is going to be this material? It is going to be this way. It will be bent, right? You cannot see this with your naked eye because why? The atoms are very small. But assume that it is a Jenga. Can you in Jenga you can see, right? So you have to assume. Are you able to understand what I'm trying to say? No? Yes, no. Okay, assume that it is like a Jenga. Okay, so what is going to happen is if you apply any force that is parallel, the top part can move, right? So now whatever the force that you are applying, that is taken as F, and A is going to be your area. Again, I guess somebody is joining. Is it no, no, I heard something. Okay, so let me erase this one and straight away I will write down the formula. Okay, the only difference is on the, I will write down sigma, and that is your shear. So S. So this is going to be your force that is parallel, right? That is parallel divided by the area. The area is going to remain the same area, right? And here it is going to be epsilon, and it is going to be S, right? So this will be what? This will be the small change. This has taken place over here, right? What is this particular distance that it has traveled? That is your delta x or delta L, anything you can take, right? So if I take it as delta x divided by the total length, so this is going to be your epsilon or S, shear strain and shear stress. So let me write down over here, these are tensile stress, tensile strain, right? Here this is your shear. Next, we have volumetric. right? And over here, what is going to be the difference? The difference is going to be again this way, right? Or I can show it like this. If I have a ball, right, and this is compressed, right, then what is going to be the force, and what is this small area that is acting on A, right? Now for this also I can write down the formula. So it is going to be epsilon, here it is going to be sigma, right? But what is going to be the difference over here? You can write sigma v, right? This is going to be your F divided by A. And here you can write down the total, right? Why total? Because in the first one and the second one there is only one force that is acting, right? But if I have to compress a particular ball, can I just put one force? No, right? Then the ball is going to be something like this. So I have to apply force in all the direction, meaning that the sum of all the forces I have to consider. So here I can write down F total over here, and a box around it. And similarly here it's going to be epsilon v, and it is going to be your delta v, now the change in volume divided by the change in v. This is the difference. Okay, so these are the main things that you have to know. Is somebody else also joining? Yes, Prajwal, you have raised your hand. Well, yes, really. Here, here, one. uh Area is the surface area it is acting on. Okay, so this is this area, whatever this area is, small area, that one. Okay, so but when you consider, you come again, your voice, I didn't hear you. Yes, tensile stress, tensile strain, tensile, shear strain, shear stress, volumetric strain, volumetric stress. Okay, so over here you should not be getting confused. Tensile and compressive both are one and the same. Okay, only the direction is different. So if you have to change something, what do you have to do? First you have to apply some force, and if you are applying some force, right, then it is going to be affecting some area. You have to apply some force to some area, and if you do that, what is going to happen? Some change in length is going to happen, or in the dimension. If it is only in one dimension, it is your one dimensional change. So that is the reason why only L is taken. Here what is going to happen in volume? The total volume will only change. That is the reason why delta v divided by delta v I have taken. Okay, instead of delta, just L. Delta is going to be the change over here. I hope it's clear. Okay, now let's move on. I told you that there are two types of material, elastic and plastic. And elastic material, they will come back to their original shape. But will this happen all the time? No, right? If I have a rubber band, yes, at until at some point it will come back. It will get restored. If I apply huge force, what is going to happen? It will break, right? So in order to get that, there is Hooks. Okay, I'll be telling you hooks about Hooks law later. But as of now, the one thing that you have to know is about your stress and strain curve. And here what can be asked is they can give you the graph, and they can give you the points and what is going to happen, right? So over here, you, as you can observe, until your A and B, or you can consider B point, right? So if you apply this stress and this much strain, nothing is going to happen to the material, and it will regain its shape. It will regain its shape. And from B to C, this is known as the lower yield point. This is very important, and I'll tell you what is this. Okay, now after this point, until this point, if you go, right, it will come back again, but it will not be the same dimension. For example, if the rubber band is like this, right, if I apply force until over here, right, until the stress is at this point and the strain is at this point, it will regain the original shape. It will regain its original shape. Now if I apply any force that is over here in this region, right, then it will come back, but it will be this way. It will not go to the original shape. It will not break. It will not break, but it is going to keep on extending. Are you able to understand? I will repeat again. Huh? Yes, yes. Right. And then slowly, slowly till the point D, the same thing is going to happen at a faster rate, at a faster rate. And at this particular point, this is the breaking stress. Breaking stress. At this particular point, almost it is done. Almost it is done. Then it requires minimum of stress and strain to break away. After a particular point, it is going to be very, very easy. However, not much questions are asked based on the graph, because this is theoretical question, right? And you'll in CET or your NEET, it is not your theoretical question, right? So this is not that much important. Now coming to your Hooke's law, right? So let us talk about Hooke's law, and I think then we can start with the problems. Okay, then yes, sure. Yes, most of the times not much questions are asked, but you can have a look. These are theory based questions. Okay, yeah, I think you had this 5 mark question, right? Explain the stress and strain graph. Okay. Now let's talk about three types of moduluses. And what is that? That is Young's modulus, shear modulus, and bulk modulus. And what is this? Young's modulus is represented by Y, and it is the ratio of tensile stress over tensile strain. So let me write down over here tensile stress over tensile strain. And we already know the formula. What is that? We can go back over here. This is your F divided by A, and it is delta L divided by L. The same value can be plugged in over here, right? Now you just have to remember that one. So what is going to be your L? You can write this as sigma T divided by what? Epsilon T. And what is your sigma T? It is your F divided by A. So you write down F divided by A over here. And here what is this one? Sigma T. It is delta L divided by L. Delta L divided by L. So this is going to be your formula, and I can simplify this, right? How do you simplify this? I guess I think you know this, right? A over B divided by C over D. This can be written down as A over B multiplied by D over C. Yeah, dividing fraction upon a fraction. A divided by B divided by C divided by D. There is some method that you have learned in your high school, I guess, which is called KCF. You keep the first fraction as it is, change the multiplication division sign to multiplication sign, flip over the other fraction, you will be getting your answer, right? So over here I can define the y. How I can write y as now? So now y is going to be equal to f multiplied by the denominator, which is L divided by A multiplied by the change. What is the change? That is delta. And this is the formula for Young's modulus. Is that clear? Yeah. Yes. Similarly, you can find out your shear modulus and bulk modulus as well. You just have to plug in these formulas and you will be getting your answer. Okay. And oh, okay, well, one second. Here, I will make a small okay. Anyway, not a problem. The same thing is there, right? Similarly, you can write down for shear and bulk as well. You just have to divide these two. These two you divide, these two you divide, you should be getting your answer. Now I will start taking the questions. The first question: what is the SI unit of modulus of elasticity? It is what? It can be Pascal or Newton per meter square, both are one and the same. So the first one should be the right answer over here. If it is given as Pascal, you write down as Pascal. If it is given this way, it is going to be Newton per meter square. Okay. And for this, you can write your dimensional formula as well. So what is going to be the dimensional formula over here? For Newton, it is force is what? Ma, right? So it is going to be ml t minus, and here we have m as well, so it is going to be m minus 2. So this will be sorry, meter, sorry, yes. So this is your Newton per meter, right? L. So L is going to be minus 2. L is going to be minus 2. This and this you can combine now. So it is going to be m L minus 2 t minus. This will be your dimensional formula. Okay. Anyway, this is not us, but anyway, I have just added. Let me go to the next question. I'll share all of this. Now, with rise in temperature, the Young's modulus of elasticity will increase, decrease. Okay, and one thing I will like to add: greater the Young's modulus of elasticity, harder it is to break the substance. Right? Lower the Young's modulus of elasticity, easy it is to break any substance. So if and you have any soft materials, right? For example, your glass will have less Young's modulus of elasticity, right? Similarly, I can take up any metal. This will have a little higher. And then we will have something called what? Alloys. What are alloys? Alloys are mixture of two or more than two metals. If we are mixing two metals, there should be some advantage, right? Yes. Yes. Why do we mix? Because we want to make it more stronger. That is why we mix. Or else we can use the same metal, right? So what are the examples over here? The best example is your steel, what we use in construction. Most of it is made up of iron, but we use other metals as well. Okay, so this is one information that you have to know. Coming to the first question, with rise in temperature, the Young's modulus of elasticity increases, decreases, remains the same. None of these. What do you think will happen? Decreases. Yes, it will decrease. Why? Because I can consider a steel like this, right? Now, if I have to deform it, it will take a large force, right? But if the temperature is high, then what is going to happen? It will not melt, but it will kind of get soft, right? The metal. Then it is going to take lesser force to form, or lesser force to deform that material. So it will decrease. It should decrease. The next question is, what is the Young's modulus of perfect rigid body? I think when I started with rotational motion, I told you what is a rigid body. What is a rigid body? It is a body which will not deform with external force. If it is not deforming, then what should be the Young's modulus? Anyone? Hi. Maximum andre ಎಷ್ಟು? It is infinity. Yeah. So you cannot deform this at all. So how much force you require? Infinite number of, or infinite force you require. But there is nothing called your rigid body. This is your ideal body, ideal condition we consider. But however, for this question, the answer is infinity. Okay, I hope you are getting it. Yes. Let me go to the next question. A cable that can support a load of 800 Newton is cut into two equal parts. The maximum load that can be supported by either parts is. So there is a cable and it can support a load of how much? F is equal to 800 Newton, right? Then what happens is it is cut like this, and then it is hung. Now what will happen to these both? The maximum load that it can support. Now how much it can support? 100, 800, 400, 1600. it will depend upon the material, right? It will not depend upon the length. So it is going to be the same thing. Whether you cut two pieces, three pieces, or 10 pieces, it can hold the same weight. It can hold the same weight. So 800 Newton is given. So the answer should also be 800 Newton. If it is 100 Newton, then 100 Newton is going to be your answer. It is not going to make any difference. They are not asking the total one, right? Then total, then it is different kind of question. Or it is just as the maximum load that it can support. So maximum is not going to change. Yes, you asked something. I think I missed. Anyone? I heard something. Okay. Let us go to the next question. Glass, rubber, steel, copper in order of ascending property of elasticity. What do you think the answer is for this one? I think I just told you over here, right? So where did it go? Did I erase that? Okay. So Young's modulus is going to be lower for the things that you can break easily, right? Over here, which we have to plug in increasing order, meaning that which is the material that we can break easily, rubber or glass. Steel and copper cannot be your answer, right? Just by looking at it, can you cancel option? I guess somebody is joining. Just a second. Anuj is joining. Is that okay? Okay, let me go back. Hmm, where is it? Where is it? Yes, here. Yes. Now, increasing property of elasticity. So, what should be the answer over here? Just by looking at it, copper and steel cannot be your answer, right? Because higher the Young's modulus, harder it is, and lower the Young's modulus, brittle it is. Option B. Okay. B. Ah, glass. Yes. Either it can be C or D, right? It should be glass, rubber, copper, and steel. Glass you can break easily, and rubber it is going to take a little more force. If you can imagine, can you pull a rubber apart? Even your small rubber, it is going to take a lot of force, right? Yeah. So rubber is going to be a little harder than glass. Then it is going to be your copper. Why copper? Because copper is pure metal. Pure metals have lesser Young's modulus compared to your alloys, and steel is one of your alloy. That is the reason why we use in construction or in any other application. Anyway, going to the next question. A wire of length 1 meter and its area of cross section is 1 centimeter square. The Young's modulus of the wire is 10 to the power 11 Newton per meter square. Two forces equal to F are applied on two ends of the opposite direction, and the change in length is 1 millimeter. What is the value of F? What is the value of F? Two forces equal are applied on two of its and in opposite direction. So they have not given whether it is compressive or tensile, right? So there is a wire, and how is your wire? I can consider this as a big cylinder, a big cylinder, right? Now there is a force. I don't know whether it is tensile or it is compressive, but they are in opposite direction. So it can be this way or this way as well, right? Both are one and the same. Yeah, come again. Yeah, no, I think that is wrong. It should be centimeter square. It is wrong. Okay, it is wrong. Somebody has raised. Okay, got it, got it. This is wrong. Okay, centimeter square. It should be centimeter square because area cannot be centimeter cube, right? Cube is for volume. Anyway, now here it is your area. This will be your area. This will be your area, and the force, I don't know how the force is. These two can be the forces because these two are equal and opposite. These two also can be the forces. Any force you can consider not a problem over here. Okay, so let me erase all of this. Okay, now coming to okay, and what we have to find out, if the change in length is 1 millimeter, what is the value of f? The value of f is asked, right? So how do we find out the value of f? From Young's modulus. Yes, what is your Young's modulus given by? Let me go back. Young's modulus is given by y is equal to fl divided by a delta a. Fl divided by a multiplied by delta a. Yeah, delta l. Yes, this is your Young's modulus. Agree? Now plug in the values, you should be getting your answer. Now how you can write f? As f now can be written down as y multiplied by a multiplied by your delta l divided by, this will go down, right? So it is going to be your l. Now I will plug in the values. So what are the values? Y, what is given? The Young's modulus of the wire is 10 raised to the power of 11. 10 raised to the power of 11 multiplied by, what is the area? Area is cross section of 1 centimeter square, right? So how much is going to be 1 centimeter square? So and this should be in what? Meter squared, right? Yeah? Yes or no? Yes, right? And here it is millimeter. So divided by I will write down first, because this is easy. Because a and delta l, it is little bit harder because the unit is different. It is 1 centimeter cube. So I know that 1 centimeter, or I can write down 100 centimeter is equal to 1 meter, right? So I want what? I want centimeter squared. So if I square this, I should be getting 1 meter squared is equal to 10,000 centimeter squared, right? Here how much is given? Here it is given as 1 centimeter squared. So 1 centimeter squared will be how much? I have to divide by 1 2 3 4, 10 raised to the power of negative 4. So I should plug in 10 raised to the power of negative 4. Did you understand how? This is very very important. I will repeat again if you want. A, what is your A? A is cross sectional area. Take this as centimeter squared. And the SI unit is what? Meter squared, right? Here it is 1 centimeter squared. So how will I convert? I know that 100 centimeter squared is 1 meter. Yeah, what I want centimeter square I have, but I want in meter square. So I will square both the sides. I should be getting 10 raised to the power of 4 centimeter squared is equal to 1 meter squared. I want 1 centimeter squared. So divide 10 raised to the power of 4 on either sides. So 1 centimeter squared will be equal to, this will go on top, 10 raised to the power of negative 4. The same thing I have plugged in over here. Did you understand how? Yeah, converting centimeter square to meter square. I will leave this over here. Next, it is your delta L. Where is your delta L? Delta L is 1 millimeter. 1 millimeter as in 10 raised to the power of negative 3. Multiply all of them. You should be getting your, so it is 10 raised to the power of negative 11 minus 4 minus 3. Yes, 10 raised to the power of 4. Here I am using the property of exponents, and this is in your Newton. Where is it? It's over here. Option B is your right. So just if you know the formula, you can get your answer, but you have to know this part as well. This is also very, very important. Coming to the next question. A thick rope of density rho and length L is hung from a rigid support. To increase in length of the rope due to its own weight is what? So these kind of question, you have to remember one thing, and I'll be telling you what is that, right? And I think when I discussed rigid body, I told you about center of mass, right? What is the center of mass? If I have any mass, right, there will be a particular point where I can assume that all the mass is concentrated, right? That is known as center of mass. That is how you can balance any stick or pen on your finger. If you know the center of mass, easily you can balance. right? Now what is given in the question is there is a thick rope and it is increasing due to its own weight, right? If it is your own weight, nothing is added, right? Then what is the weight you have to consider? You have to consider the weight from where? From the center of mass of that particular rope or whatever it is. Now here there is a rope given, so let me write down a rope this way, right? And it will be in form of a cylinder, okay? And density is given, the length is given, it is L, and it is hung. Increase in the length of the rope due to its own weight, due to its own weight. So what is your weight? Weight is your mg, right? And it will act downwards always. And from where you can consider this? You can consider this right from the center, and this will be your center of mass. It will be your center of mass, right? Now what you gotta do? You gotta plug in the value of y. You see y over here, Young's modulus is given, right? Y is the Young's modulus. So first I will write down what is the Young's modulus. I know that the Young's modulus is the ratio of sigma over rho. And what is your sigma? Sigma is F divided by A. You can write this as small big A, okay? Because small a is your acceleration, right? And here it is your delta L divided by L. And now this can be written down as what? It is your F multiplied by L divided by A multiplied by your delta, right? Now what do I want over here? The increase in length, increase as in your delta L, by how much it will increase. This one, this is the length I want, right? Now I will send all the other terms to the left, right hand side, and delta L over here. I should be getting my answer, right? So y is equal to FL divided by A delta, delta L. So what is going to be your delta L equal to? It will be equal to FL as it is, and your y and A is going to be multiplied, right? Now what is your F? F will be due to its own weight, right? So it is going to be your mg. So you can plug in mg over here. Yeah, I hope you are getting it. Yes. So force is equal to mg because it is, because of its own weight. So force will be equal to mg, right? Now what do we have to find out? We can plug in the value of area as well, right? Y as it is, area as it is. So let me write down divided by y is it given, so y as it is multiplied by area. What will be the area over here? Area is going to be this one, right? This is going to be a circle. Circle area is pi r squared. So you can write down pi r squared over here. I hope you're getting it. Yeah. Okay. And F is what? F is your mg. So G I will write down as it is. But do we know what is your M? M is not there, right? Here. Is it there in the formula? Do you see? I mean, in the options. It is not there, right? But do I know? Do I know that density is what? This is mass divided by volume. It is mass divided by volume. Now you can easily find out what is going to be the volume of this one. What is this? This is a cylinder, right? Yeah. So rho, can it be written down as m divided by cylinder volume is pi r squared h. And here h is going to be what? H is going to be your L. Height is going to be equal to the length, right? So this can be written down as L. This can be written down as L. I hope you are getting it, what I am trying to do. Yes. Now, what will be m equal to? I have to substitute for m. M will be equal to rho pi r squared multiplied by L. That one should be plugged in over here. Okay? I hope you are getting it. And what is going to be the volume it is affecting? It is going to be from the half of it, right? From this one. This is the part that is down from the center of mass. From the center of mass. So the total mass is going to be half of it. This is going to be the total mass, right? But I have to consider half of the mass. So I can write this as rho pi r squared divided by 2. Now you cancel all the values, you should be getting your answer, right? Pi r squared is getting cancelled, right? Anything else that we have? Oh, over here we had L as well. We had L, right? So we have rho, we have G, we have L, and we have 2 over here, and we have L, right? So what is going to be the answer? The answer is going to be this one. B is going to be your right answer. Yes, this one and this one. L is one L which is already over here, and one L which is here. This one. Ill. I can write it this way, or L1 L1. This one also I can write. Okay. One of the L from M I'm getting, from M, because total length L, total length L, okay? And one of the L is in the formula itself. See over here, L formula is there. So just plug in the values, you should be getting your answer, and the second one will be the right answer. Okay, it is rho G, rho L square G divided by 2y, 2y. Let me go to the next question. A thick uniform rubber rope, of density 1.5 centimeter per cube, and the Young's modulus 5 multiplied by 10 raised to the power of 6 Newton per meter square, has the length of 8 meters. Okay, when it is hung from a ceiling room, the increase in the length due to its own weight is going to be equal to what? It is similar to the previous question. Yeah, it is similar to the previous question, right? So first, what you have to write down? First, any problem from this question, straight away start by writing down what is your y. Okay, and one more thing I will tell you. One more thing. What is your y given by? It is your fl, right, divided by a delta l. And whenever these kind of questions are given to you, by these kind I mean due to its own weight. If it is given due to its own weight, then what you have to do? Y will be y divided by 2. Just half of it is enough. Just half of it is enough. You can use this trick. For however, for the last problem I have told you how to solve completely, right? And here you don't see any numbers, right? Do you see any numbers over here? By numbers I mean density, any value is given. L, is there any value given? No, right? L, A, only they are variables. But these kind of questions where the value is given, you can use the trick. And what is the trick? Own weight, if it is given, take y as y divided by 2, right? So what is your y divided by 2? It is going to be your fl divided by 2 a delta l. Use this now, and you should be getting your answer. What do you need over here? When it is hung from the ceiling, the increase in length is what you want, right? So there is a thick uniform rope like this, and this is going to be its area. And area, is it given to you? Area, is it given to you? No, no, it is not given, right? So how do we find out if the area is not given? Or we can somehow find out the area. Yes, yes, you can do that. You can do that. You just plug in the value, you should be getting your answer, or you don't break your head. What is your delta l is what you have to find out, right? So delta l you should send over here. So let me write down delta l, which is going to be equal to f multiplied by the original length, right, divided by 2 multiplied by a multiplied by y, right? Now how can I write this as, because the area is not given to you, right? But somehow I can write down the area. How can I write area as? Can I write volume as area multiplied by length? For example, if I have a cube, what is the area of the cube? If the side length is s, it is s cube. Can I write the volume of this particular cube as the base area? What is the base area? This is a square, so s square. S square multiplied by the length, one of its length, it is going to be the volume. Can I write it this way? Yeah. So what is the volume? The formula for volume is area multiplied by length. I will be using this particular formula. Okay, because area is not given to you in the question directly. Okay, I hope you are getting it right. So I will introduce what I should be introducing your rho, that is your density. So I can write this as ma or mg in this case. So it is going to be m as it is, and instead of that I will be plugging in your rho, m and rho, right? And this is your l divided by 2 ay as it is, right? Now again, this can be written down as rho multiplied by vg, because v is going to be the volume, and here it is going to be your l, and here I can write this as 2ay, 2ay. Now I can cancel your a, because what is your a is v divided by l, a divided by l. Yes. So you can again simplify this as rho and v as a l multiplied by your g and your l as it is, divided by your 2 and a y. Now you simplify, it is going to be your rho a g l, and l is l square, divided by 2y. A and a can be cancelled out. Okay, I hope you are getting it now. Here sorry, this a is cancelled out, right? So this should not be written. A rho g l square divided by 2y, this is what I'll be left out with here. A and a will be getting cancelled. I didn't have a, so I have cancelled a. Now you plug in the values, you should be getting your answer. Density is given, yes, it is given. Yeah. 9.6, we will check. What is this? It is your 1.5. mm, I can multiply 1.2 grams. It is grams. So kg, I have to multiply kg as in divided by 10 raised to the power of negative 5,500, or I can transfer it directly, right? So it is going to be 10 multiplied by or 10 is 8 is given, 8 meter. So 8 squared, and what I have to multiply, 1000, here it is 1.5 centimeter square, right? So 1.5, it is given in centimeter, and how much is this going to be in meters? It is going to be 10 raised to the power of negative 4. I think I showed you over here, this one, right? So it is 10 power 6. No. Or I can just consider adi beda. So based, because if I consider this, I think it is going to be a problem. 1,500 directly I can consider, because four of the decimal places andre ಇಲ್ಲಿ three decimal places is going to come, and here it is going to be, yes, 10 raised to the power of 5. Yes, 10 raised to the power of 6. Yes, you are correct. So here it is going to be 10. So this two and this one will be getting cancelled, and here what we have, 64, right? So the final answer should be 64 multiplied by 1,500 divided by 10 raised to the power of 6. This will be the right answer. Check what is this answer. If I have a calculator, I will check over here. 64, 15 is 96. So 960. Wait, or I will do it this way. What are the options? 1,500. Illa, no, I have taken 10 raised to the power of 6, right? 60. Okay, we will check. See, 1064 multiplied by 1,500 divided by 10 followed by 1 followed with 6 zeros, right? So what is the answer? 0.096. 0.096 as in it should be what? 10 raised to the power of negative 2, na? Yes. I should bring this decimal to over here, right? Here. Yes. So I will multiply by 100. So what is going to happen? It is going to be 10 raised to the power of, sorry, 9.6. If I multiply by 100, I should divide by 100 as well. So the answer should be the first one. First one will be your right answer. Okay. Again, I will repeat this thing. The conversion from centimeter to centimeter or centimeter cube to meter as well. Okay, which is very very important. 100 centimeter is equal to 1 meter. Okay, now square on both the sides, you will be getting 10 raised to the power of 4 centimeter squared will be equal to 1 meter squared. Next, square again. What is going to happen? 100 centimeter, 10 raised to the power of 6, right? Centimeter cube will be equal to 1 meter cube. This is the change that you have to know. Is it clear? Here what is given? Centimeter per 100, it will be 10 raised to the power of negative 6. This will be equal to 1 per meter cube. That is the only difference. I directly have taken. Okay. So I will leave this as it is. This will be useful for you. Let me go to the next question. A steel wire of cross sectional area. Here the area is given to you, right? So not a problem. A steel wire of cross sectional area 3 multiplied by 10 raised to the power of negative 6 meter square can bear a strain of 10 raised to the power of negative 3. Young's modulus of steel is 2 multiplied by 10 raised to the power of 11 Newton per meter squared. The maximum mass of this wire can hold. Maximum mass this wire can hold is what? Right, so there is a particular wire which is given to you and few of the information are given to you, right? Maximum mass that this can hold, what is going to be that? That is the question, right? So if we have any mass due to gravity, it will experience a force mg, right? So if this particular wire can withstand this mg, then it will not break. It will not break. If this particular force is greater than this wire, then it will break. This is the basic idea. Yeah, I hope you are getting it. What is the basic idea of this question? Yes. Okay, now I told you, any question from this particular chapter, what you have to do, you have to start with your Young's modulus. What is your Young's modulus given by? It is your sigma divided by epsilon. Sigma divided by epsilon, right? What is asked over here? Maximum mass is asked. Yeah. Yes. So first I will calculate the maximum strain. Maximum strain is given to you, right? Maximum stress I will calculate, right? So what is going to be the maximum stress over here? Can I write this? It is going to be equal to sigma, can be written down as y multiplied by epsilon. Yeah. Now I will find out these values first, right? It is going to be what over here? Young's modulus is already given to you. Is it given to you over here? 2 multiplied by 10 raised to the power of 11 Newton per meter square. And what is your epsilon? It is multiplied by 10 raised to the power of negative 3. Negative 3. 11 minus 3 is 8. So what is going to be your rho? The value of rho is 2 multiplied by 10 raised to the power of 8. Again, it will be Newton per meter square. Did you understand how I have got the value of rho from Young's modulus and epsilon? Because both of them were given to you over here, right? Yes, y was given to you 2.0 multiplied by 10 raised to the power of 11, and epsilon is 10 raised to the power of negative 3. You have to find out your rho and This is your sigma. Yeah, this is your sigma. Did I tell anything wrong? I think I misspoke. I'm sorry. This is your sigma. Okay. This is your epsilon. What is this? Stress. Stress. Yes, sigma stress. This is epsilon or strain. Strain. Okay. These two are given to you. So just using this particular relation, I can find out the value of sigma. Now let me go back to the question. What is that they have asked? The mass is asked. Mass is asked, right? So what is going to be force? How can I write force as? It is going to be stress divided by maximum stress divided by area. Can I write it that way? Stress divided by area, right? And here I can write mg will be equal to F. So what is your m? M is F divided by G. So I have to find out the value of F, because I know that G can be taken as 10. G can be taken as 10, right? Now, how do I find out the value of F? It is going to be stress multiplied by your area, right? So F can be written down as your stress multiplied by your area. Yes or no? Because this is F divided by A, right? I hope you're getting it. Stress is F divided by A. From here, I can find out the value of F. That value of F I have to plug in over here, right? So what is the value of F? It is 2 multiplied by 10 raised to the power of negative, positive 8 multiplied by 3 multiplied by 10 raised to the power of negative 6. It is given over here, cross sectional area, a steel wire of cross sectional area, right? So when I multiply, what is the answer here? It is 6, right? And 10 raised to the power of 2 multiplied by 10 raised to the power of, right? Now you divide both of them, you should be getting your final answer. What is the final answer? M is equal to F, 6 multiplied by 10 raised to the power of 2 divided by 10. And here it is going to be 10 raised to the power of 1. This one and this one can be cancelled out. 60 kg will be your right answer. Have you understood how I have gone about this question? Any question from this particular topic, start with your Young's modulus. If you know few relations, easily you can solve these kind of questions. Okay, going. Okay, these are the questions that I had considered. All right. Anyway, I will be sharing the screen. I will be sharing this particular file with you. Okay, where the questions clear what we have solved. So most of them will be your numericals itself. Now you can take some break, and then we will be starting with the next one. I think I have taken oscillations, right? We can take about 5 to 10 minutes break, and then you can. Or are you bored for today? No, Prajwal says no. It's thumbs down. So if no, then I'll continue tomorrow. If not, I can continue after about 10 minutes. You can just type in your yes. Somebody has told Adawaga. Okay. Yes or no, you type. If you are okay, I will. You can continue, says Prajwal. Okay. Okay. Others also can.